shy and mute when I'm with her. I am an inarticulate, bashful boy.
If my heart could only find a voice.
If my heart could only find a voice, she'd hear something new and thrilling. Would she box me
Oh, nothing like Jerome Kern and that tremendous performance to start a show. Welcome to the Evidence and Reasons Academy. I'm Salvador Cordova, and this is going to be Nerd Torture. Glory and honor to our Lord and Savior Jesus Christ. This channel does tend to cater to Christian students, and especially in the sciences, in college, graduate school, and beyond. So this shouldn't be at all very surprising what we go through, because you students out there know what it's like to just struggle through scientific curricula. It's not fun unless you find torture fun. So what are we going to cover today? I don't know. See how far I could get through stuff. Let me share my screen here. See if I could get this going. This is a page out of my General Relativity book, and it's early on, and I'm just like, oh my goodness, it's been so long since I've done this. I mean, this is like 10 years ago. This is how the Lorentz transformation is represented in General Relativity, and you could see kind of the convention here. Oh my goodness. I have the privilege of seeing Dr. Phil tomorrow. That Dr. Phil is not Phil the psychologist, but Dr. Philip Dennis, an expert in general relativity. He is published in the Physical Review Letters, which is the #1 physics journal possibly in the world. And he's going to be teaching me relativity. Now, I had it in school, in grad school, but oh my goodness, I totally forgot everything I learned after 2 weeks. It was an insanely difficult, well, it wasn't insanely, it was difficult. The insanely difficult course was classical mechanics, oddly enough. The way classical mechanics was taught in my school, right out of Goldstein's Mechanics, was just miserable. I would say the next hardest class would be mathematical physics, which they titled Mathematical Methods. It was also taught by Dr. Philip Edelman, so I call him Dr. Phil, the other Dr. Phil. And oh boy, that was hard. I would say the way general relativity was taught in my school was not too bad. The easiest course was just an introductory course in modern physics. I thought astrophysics was the easiest, the next easiest class. The professor didn't pounce on us too hard on that class. Plasma physics was pretty tough. Statistical mechanics and thermodynamics would probably be about third on the list, but it was a good class. I did not like my solid state physics class. And cosmology was modestly easy. The professor wasn't too hard. Quantum mechanics would be about number 4. So in order of difficulty, it'd be classical mechanics, then mathematical physics, which is mathematical methods. Number 3 would probably be maybe general relativity, and then statistical mechanics and thermodynamics. But that was a fun class. Plasma physics was up there, so I'm going to have to put plasma physics higher. I'm sorry. So that'd be classical mechanics, then mathematical methods, then plasma physics, then general relativity, statistical mechanics, and thermodynamics. Quantum mechanics, cosmology, astrophysics, modern physics, kind of in that order, something like that. I mean, it's been a while. I'm grateful for the education, but I've unfortunately forgotten so much. I mean, I just looked at this notation here, and I'm like, oh my goodness, I don't even recognize half of it. I mean, goodness, I'm so embarrassed. I've so forgotten this notation, and I'm going to have to relearn it. So this is a set of 4 numbers. That's a tuple, and the little symbols and little enhancements have a meaning. Like I don't know why that has a 0 or a bar over it. Goodness, totally forgotten. I'm really embarrassed now. I have to relearn this. See, like you could see here, this lambda with the alpha and the bar, and then the beta here, subscript, is a collection of 16 numbers. I'm just like, holy smokes. It's been a long time. It's tensors and one forms. I'm going to have to crawl through this. And Schutz's book is, this note. He uses a different convention than some of what I see. I'm going through this book by Bondi. Do I have it here handy? One moment. Oh. Bondi's General Relativity, Common Sense Approach to Einstein. And I'm going to meet Dr. Phil tomorrow. And I just feel this is kind of depressing. Unless one is working with something like at least regularly, the skills go out, and the general relativity is so alien to any other kind of physics. You just lose it so quick, because the notation that I have been using in algebra has just been like there forever, and then same for calculus. It's not too bad because I've used it so much. But the notation in special relativity for the formulas is just so alien to anything else in physics. You have to get used to thinking in new notation, and it's really it's like hieroglyphics. And the superscripts and subscripts have different meaning than you traditionally do in other fields of mathematics. So, like a superscript is not necessarily a power, and you have to be really careful. And then there are different notations for derivatives. And, there are these things called Christoffel symbols, and just like, oh man. And then you have these tensors, like Riemann tensors and Ricci tensors. And it gets a little bit hairy. Now, professionally, what people do is they will use Mathematica, because sometimes pumping this through Einstein field equation is really tough. But I'm not even going to go immediately there. I'm going to revisit special relativity. I had some questions. You've heard me put this on the table before. The thumbnail you all have seen. A lot of special relativity is not taught straight from, you can build up special relativity by starting with electromagnetic theory, and that is kind of painful. I had, that was my first, I'll never forget, that was my first day assignment. My first day of grad school, in my first homework assignment, I had to do this derivation here. And having to do it from scratch is pretty tough. The professor kind of spoon-fed us a lot of the pieces where we would get stuck. He set up a lot of the derivations, so all we had to do is some calculus and some algebra, and it was being solved. So, good night, Rebecca. Thank you for gracing my my stream tonight with your presence. So, good night, and God bless. So, Where to begin? I'm going to have to also learn to use Overleaf Latex. So Jonathan Bartlett, who had joined me before, was working with me. He's going to help me publish some of my teaching materials that use a lot of this math. And let me put on my glasses so I could see my distant screen. Latex evolved. The easy-to-use online collaborative latex editor. So I'm going to accept all cookies. Let me turn off my display capture in case I have to. It says register using Google. And I'll register it under ER Evidence Reasons Academy. Let's see, it says try premium for free. Nope, it wants money. So I'll just skip. New to latex, start by looking at our template or latex help guide. So start my first project. Now I'll do a blank project and I'll call it test. Create. So let's learn how to write equations. Edit in the left pane, click recompile to see the PDF output on the right. So I put on my glasses. I'm getting half blind here. Oh, nice. So now let me see if I can grab a PDF file. See, now I might have a means of handing this off to the publisher or the print, the printer people. So Dr. Dennis and I and one other person or a couple others are forming the Creationist Cosmology group. And there's really just going to be a lot of basic study. You know, some creationists are so eager to solve all these problems, and in young Earth creationism, and really, it'd be good if collectively we just started learning basic stuff like general relativity. And I've got such a long ways to go to relearn what I've long since forgotten. The good news is I have studied it, and I got through the class. The professor with an A. My professor thought I was adequate, and you know I have a really good short-term memory, and and that serves me well, at least as far as grade-wise, but I forget things so easily. So it says here, now let's do a recompile. So I took, let me see. I'll show you what I'm doing. So I had an equation here, right there, and it's colorized. And then I took, converted it to that, and then I cut and pasted it into the Overleaf, and I'm going to do a recompile, see if it takes it. Missing dollar inserted. So where do I put the $sign? Do I need to put a $sign? Okay, now let's try to recompile. And it's so tiny. Okay, I have to find out how to make this bigger. I want to make the equations bigger. It doesn't tell me how to make this a bigger. Rich text. Oh, good. Maybe I can do this. Will it let me colorize? That's the source text. And then the rich text. Okay, I can do bold, inline math. Let's look for font. I'm gonna have to have a session with Johnny B. He spent a lot of time trying to get me to understand this. Let's try this. Large. Okay, let's do a recompile. Didn't make it large. Alright, I'm going to look for latex symbols for coloring. Oh, this is going to be a pain. Okay, so let's try this. Text color or GB 1 0 0 and then that and then that. Now let's recompile, see if we get it to turn red. RGB. RGB. What did it not like? Does it really want that? Okay, it turned it red. And it renders PDF and I have one warning. Where is the undefined control sequence? Okay, let's try to remove this. See if that does anything. Didn't seem to complain that time. Well, it'd be helpful if it explained. What the problem is. Why am I getting an undefined control sequence? Okay, let's just put the number 1 in here, or 0. Okay, let's do a recompile. See, I'm going to just take this straight out of the book, and it doesn't like it. So let's remove the $sign. Let's recompile. Didn't like that. How about that? Missing $sign. Okay, so I'll put a $sign here. How's that? Okay, I'll put a carriage return. Just does not like. Okay, using colors and overleaf. Okay, so let's try this. Flash color. Forest green. Okay, let's recompile. See if it'll take it now. Okay. So let's try to change this. Use package. Let's recompile. No, we are getting a little motion now. Okay. So I'm looking at this overleaf thing here, and it'll be font size. Okay, so Oh man, this is so... Okay, so let's try this. Boundary. Huge. Okay, let's recompile. That wasn't helpful. Slash huge, huge. See, I'm gonna just take this and put it here. Let's recompile. Nothing. Do I need to include a package? I mean, I wanted huge. Man, that's disappointing. Why can't it render? it to go huge once. Let's try this. It's not doing a thing. I'm going to remove all of this stuff here. I think I could use Johnny B's help. I'm going to try to get an overleaf example. This is really aggravating. It's not explaining why I can't do certain things. So now we'll use a man, that is so hard to read. Okay, and I can do this. Let's recompile. Okay, I now understand a little bit. And it's still the same size, even though I specified huge. It's aggravating. That's ridiculous. It's just ignoring it. Yeah, I used the qualifier huge and it doesn't make it huge. let's try this. Let's compile. Aggravating. Okay, let's do begin math and math 1 plus 1. Now we're getting somewhere. Okay, so slash color red. Okay. See, this is ridiculous. It wanted me to put a see, this is ridiculous. it's giving me these stupid compile errors. I need to get a document. This is just like next to awful how bad this is handling this. It's unbelievable how bad this is handling all of this. Okay, let's recompile. See, this is unreadable right here. The equation has to be bigger. That's just ridiculous. I mean, I also need a little bit more separation of space here. See, that's ridiculous. I can't even put a space. That's absolutely ridiculous. Do this, see if that'll give me a line space. Okay. Okay, let's me do it if I do a double line. So try it this way. Oops, that is a slash frac. Okay, now let's try slash huge. man, this thing's really messed up. This thing's really messed up. Oh man, this Overleaf. I'm gonna have to write Jonathan Bartlett. I can't make heads or tails. I'm gonna have to write Jonathan Bartlett to get this fixed. This is miserable. Oh, hi Mark. Yeah. I actually did Google for directions, and the directions aren't doing, I actually cut and pasted it right into the document and it's not working. So I'm just going to write Jonathan Bartlett. He's a professional publisher. I'm hoping he'll help me fix this. This is getting to be too painful. There's probably a simple fix, and so what I'm going to do is write him right now. So hang on, I'm going to send him a letter. I'm going to type, I have another computer on this screen here. I'm going to send Jonathan Bartlett a letter. Okay, subject to Jonathan Bartlett. Jonathan Bartlett was here before on this channel. He was talking about derivatives, and I'm saying, hi, can we set up a hopefully brief session to work on Overleaf? I got to trying it, and it's not rendering the way I expected. It's probably something trivial. Thanks again for dinner in Dallas. Sal. I said, can we set up a brief live stream session to help me iron out some problems with Overleaf? I got around to trying it. And it's not rendering the way I expected. And the editor is doing, and the compiler is doing some funny things. Okay. So there's also math jacks, yeah. Can we set up a brief live stream session to help me iron out some problems with Overleaf? I got it only partially working. I got around to trying it and it's not rendering the way I expected and the computer is doing some funny things. Thanks again for dinner in Dallas. See you at the CELS conference in June. Okay, so I just sent him a letter and I hopefully will get word back on how to get this. See, I got this working in Microsoft. See, I'm able to get this to work nicely in, well, not so nicely. Microsoft has some other problems, has another set of problems. So, okay, so I have this in Microsoft. And you could see I can convert that coding and it's slow. I can convert that to look like that. And that's what I want. But it does some really screwy things that's just brutal to correct. And I can convert this to a PDF file. But this is just, Microsoft has some real peculiarities that are just miserable. And yeah, Overleaf is the system Johnny B is recommending because he runs a publishing company. He likes to have his stuff in Overleaf. He doesn't like it in Microsoft Word. And so we're just trying to resolve how to get this off to the formatting or printing outfit that runs his journal. And his journal just makes beautiful layouts. The text can look really plain, but once it gets in that print format, it looks beautiful. So, see, the sizing of this is kind of hard. And most of the aggravation in putting this together had nothing to do with the math. It had a lot to do with the way Microsoft formats things. And then it just kind of rewrites the equation. I'll enter an equation like that and it's going to rewrite it. It's just aggravating. It does this. See, it totally, look. See, it did an autocorrect and it just changed my equation. That is so aggravating. And I didn't change, that's just, oh, goodness. I don't know how I kept my sanity. And then Overleaf's doing kind of the same, a different set of screwy things. And the coloring is what makes this workable. You can actually see all the variables in colors, and it helps do the calculus a little more straightforwardly. And so I'm going to have to talk to him how to get this squared away. I'm sorry. See, I was complaining here that when I change this, when I'm editing this in Microsoft Word, it'll do an autocorrect on my Latex. So I'll do this. Okay, and then when I bring it back to the Latex, sometimes it's just going to render it funny, and it's like that wasn't because I entered anything new. It's just deciding to rewrite what I wrote, and that's really aggravating. But when I can get it to work, I can get it to colorize. Now, Overleaf doesn't colorize very nice, so I mean, I know how to write Latex, but the way Overleaf implements it, it doesn't render, and then Microsoft Word doesn't render it very nicely either. But I can get all the nice colors, so I don't know what's going on. Because I looked at some of the instructions for the Overleaf Latex, and it's just, I'm gonna have to talk, I have to talk to Johnny B, see if we can, because he said that he might not be able to accept my paper, not because of content, but because of just like the publishing, kind of these obnoxious publishing details, because he wants to have it in an Overleaf, and I can't get it. I can't take these Latex equations right here and get it to look as nice in Overleaf as I have it here. So this is how it will look in Latex, and then I'm going to convert it to the equation format. And see what it did to all the partial derivatives? I didn't change anything. It changed my Latex coding. That's what's so obnoxious about Microsoft Word. I mean, it's not supposed to do that, but it does it all the time. That's really aggravating. I mean, I don't know how I didn't lose my sanity because Microsoft kept doing that to me. So at least Overleaf doesn't do this autocorrect that just destroys what you wrote. I mean, whatever's in Microsoft Word is just terrible to handle equations. And yeah, look, see, all I'm going to do is, this is my equation, and it's supposed to reveal, when I say linear, it's supposed to reveal the Latex coding. I'm not going to edit it at all. I'm just going to get it to supposedly go back to the equation. And you could say, instead of the partial derivative, that little kind of backward 6, it says partial. So then I just have to undo it. And I don't know how I didn't lose my sanity having to deal with this. Yeah, laugh out loud. It was terrible, Mark. Okay, so, that's about all I'm going to do for now on this. I'm just going to have to wait on Johnny B. Otherwise, I'm just going to lose my sanity. I probably wasted 2 days just wrestling with Microsoft issues, getting the editor to work. It's just aggravation. I'd rather be spending my time actually doing something real, not fighting with an editor. So anyway, I'm not going to go read from Bondi here. And I have diagrams from Bondi. Let's see if I could show them. I'm going to show it here. I'll get this rotated. Okay. I'm going to read page, I can find it, because Dr. Dennis is going to work with me tomorrow. Figure 13, so this is figure 13. Oh, this is figure 12, I'm sorry. It will be remembered that Einstein's principle of relativity asserts the equivalence of all inertial, uniformly moving systems. Newtonian dynamics already stresses the importance of acceleration and the irrelevance of velocity. Pouring tea in a smoothly flying jetliner is no more difficult than in one's home, and so defines inertial systems. It asserts the equivalence of these inertial systems as far as dynamics goes. Dynamics involves force. Force is dynamics. Whenever there's force, there's dynamics. Absence of force would be kind of like statics. But earlier chapters in stressing the unity of physics showed how awkward it would be if different parts of physics were governed by different rules of transformation from one inertial observer to another. Thus we were led to Einstein's principle of complete equivalence in all inertial observers, and now we explore its consequences using simple experiments. And I have said I actually don't think the first postulate, so what they call the first postulate, that all the inertial observers are identical, I don't believe that. I don't believe that, because quantum mechanics demands absolute time, and that means all inertial observers cannot be equivalent as a matter of principle. But in any case, it will be useful to depict our moving observers, to use the jargon of the theory, on space-time diagrams in figure 12. In such a diagram, the vertical axis represents time. So this is the vertical axis. So that's time 1, 2, 3, 4, 5. So call it seconds or whatever. Measured by some inertial observer, and the horizontal axis represents distance. Fortunately, almost all our arguments require only one space dimension. All bodies considered move along one straight line, so this representation is sufficient. The relationship of so now I'm right here at this paragraph. The relationship of inertial and moving observers. Since the observer A is the one who draws the diagram, he understandably will make himself the origin of the coordinate system. That is to say, he will begin making his observations at his own time zero, and will measure the position of other observers in both time and distance from his own position at his own time zero. Because he considers himself to be at rest and thus is not going anywhere along the distance axis, his x-coordinate remains 0. Distances along the t-axis represent change in time. Show the progress of A in the diagram of the experiment. And it should be remembered that it is A who is measuring the distances along T. So now let me show the other diagram. Let me rotate this. Oh, that made a double shot. Okay, rotate. So this is in figure 13. Let me get something to drink. My throat's killing me. I'll be right back, guys. Oh boy. Oh, thank you. I got a piece of tiramisu. It tastes so good, just to kind of soothe the soul. I got it from Giant tiramisu. I got it from the fridge just now in the kitchen, but I bought it from Giant. It's kind of pricey from Giant. The Walmart one's pretty good. Never heard of them. We don't have a public store here. Anyway, tiramisu is my favorite dessert ever. Okay, so it says here, for example, to plot the position of B at time 0 plus 5, say, and at a distance of 6 units from himself, A will count of 5 units on the t-axis and 6 units along the x-axis. So we have B here, it'll be 6 units. So it looks like B is already kind of starting here, and then it ends up here after 5 seconds. And then this line is the speed of light. You know, this is the thing about relativity. All of the all these diagrams are just kind of strange. You know, it's just not like classical. They use a sweet coffee on the bottom. Just go to sleep already. Okay. A, thus, in relation to himself, has established B's position at a given time and distance. Since B2 is an inertial observer, he is, by our definition, traveling at a constant velocity, and in equal intervals of time, he will travel equal distances. Hence, all B's positions on the space-time diagram will be found to lie on a straight line, and any other inertial observers likewise can be represented by straight lines. Kiev cake is better than tiramisu. Yeah, I should turn in soon. It is 2:52 a.m. here on the East Coast near Washington, D.C. Figure 13 is a space diagram of A and 4 other observers, and that would be B, C, D, and E. The steeper the line, the less does x change for a given change of t, and hence the slower the motion, the less distance covered in a given time, the observer relative to A. Thus B moves away from A fairly slowly and C rather faster. So the tilt of C is more steep than that of B. C is more tilted than B, so therefore C is faster. So I guess that slope is kind of the rate of change per unit time. Man, this is so bizarre, because usually time is almost always on the x-axis. Now it's on the y-axis. That's what's just so bizarre. usually time is on this axis, and then position would be on this axis or something like that. This is just reversed. Time is on the vertical axis, and the horizontal axis is position. Yeah, they changed time on you. And this is where I get so screwed up, because it's so backward. Okay, this is the space-time diagram. So A is in this position, C starts in that position, but C has a constant velocity from A. So you could see that it's farther from where A is at that point. Now, I don't know why C doesn't go all the way up there. Huh. All right, that's something to ask Dr. Phil. I'm going to ask Dr. Phil that tomorrow. Thus B moves away from A fairly slowly and C rather faster, while E, whose x-coordinate is constant, is at rest relative to A. Both B and C move away from A, since at later times, higher up on the diagram, their x-coordinates are greater. On the other hand, D approaches A. Light being very fast has a rather steep slope, and a dashed line is supposed to represent the journey of a flash of light. So this is light here. So these are somewhat relativistic speeds here when you get a bend like that, because you could see C already is approaching the slope of the light speed line. I just remember that the speed of light equals 45 degrees on a space-time diagram. And I gotta confess, I'll make you a confession here. I got through general relativity without ever doing a space-time diagram. I mean, my professor was just, Mr. Symbol processing, I mean, seriously, in my GR book, I think there was only one space-time diagram, one or two, and he never emphasized it. Let me see. Do I have it handy? I had it handy recently. It's really funny. Oh, we had some space-time. I'm sorry. So, I mean, I got through it just enough to take the exam, and then I totally forgot it. So, I did have space-time diagrams in my book. But he didn't really test us on it. I mean, my professor just loved them. He just loved tensors. He just loved tensors. Goodness. Yeah, so I stand corrected. I did have tons of space-time diagrams. This is Schutz's book. And I've forgotten so much. It's pathetic. I've forgotten so much. I don't even remember why we had these hyperbolic diagrams. Forgotten all this. So now I'm going to have to relearn all this. Yeah, we did have... I think that was it. After the first chapter, it was tons of tensors. Just tons of tensors in one forms, and I've forgotten those. And oh goodness, the stress energy tensor, and then general fluids. Gosh, I never understood the stress energy tensor. Tensor algebra and polar coordinates. Oh man. Then, after all this tensor algebra, we finally get to Riemann manifolds. And I actually did okay with the Riemann manifolds. Partly because when you just have kind of rote procedures that, you know, you see these symbols, you do this operation, it's very kind of mechanical. Not very, if you can memorize the procedure, it's not too bad. It's not, you don't have a lot of conceptual stuff, and some of it was just so tedious. Those Christoffel symbols were just like all these derivatives, and you just had to do kind of accounting, and then the professor said, okay, you know, in practice what you'll do is you'll just load this up on Wolfram Mathematica and let that kind of do all the crunching, all the symbol crunching. So let me put this in my library shelf here, and I'll have another bite of tiramisu. That's just comfort food, so let's get back to this. Biology's so much easier. Biology's so much easier than this. Okay, so Mr. Jetty said, just remember the speed of light equals 45 degrees on a space-time diagram. Light is a wave phenomenon. In chapter 5, we investigated, and you can see it here. Here's a bit of the text. It says, in chapter 5, we investigated another wave phenomenon, sound, and in particular the Doppler effect, the difference between pitch of a wave when emitted and when received due to the relative motions of the source and listener. In the case of sound, it will be remembered it was necessary to know the velocity of the transmitter relative to the air and the velocity of the receiver relative to the air. In the case of light, there is no such thing as the air. And so all we have to know is the velocity of the transmitter relative to the receiver, supposing both to be inertial, therefore moving with constant velocity. Okay, so this, I get this space-time diagram, sort of. Okay, that's not so bad. Thank you, Bondi. And now this one. Sorry for the little bit of a tilt. Okay, so now let's suppose we have two observers a constant distance apart, and that the first observer, called Alfred, so here's Alfred here, flashes an electric torch at regular intervals. And I read this before. That flash is colored white, I think, purely in order to have a definite interval to talk about, and without any special significance attaching to this value. We suppose him to flash his torch every 6 minutes, as measured by his watch. So he's going to fire off these flashes, and the flash will start to arrive. He has a train of flashes that's going to hit the spaceship where David is. Stationary, receives a flash every 6 minutes. Yeah, Alfie's talking to a UFO. Okay. Then the light from each flash travels across to David, the second observer. Since the distance between them does not change in the course of time, it follows that each flash takes the same time to travel. Thus, if Alfred flashes his torch every 6 minutes by his watch, then these flashes will be received by David at equal time intervals, also 6 minutes apart, by David's watch. As we assume Alfred and David to be a good long distance apart, it takes each flash 10 years, remember this is an idealized experiment, to reach David. But the significant thing is that the flashes, however long in transit, arrive at intervals of 6 minutes. There's nothing out of the way, and the roles of the two observers could easily be interchanged. So, if it takes 10 years for him to fire off his torch, and David will receive that flash 10 years later, that means they're separated by a distance of 10 light years. Yay. Okay. There's nothing out of the way in this, and the roles of the two observers could easily be interchanged. Next, suppose we have a third observer, Brian, traveling quite fast from Alfred to David, who remain at rest relative to each other. See figure 15. The reader is advised to open this figure and leave it constantly available while following the argument. So there is Brian right here in the spaceship. There's a little spaceship here. Brian, while traveling from Alfred to David, also watches these flashes. As he moves away from Alfred, every successive flash has to travel farther to reach him than the previous one, and is therefore longer in transit. Accordingly, by Brian's watch, the flashes will not arrive every 6 minutes, but at longer intervals, simply because each flash has a greater distance to cover than the preceding flash. For a suitable speed, which we will not work out now, we may suppose the flashes are received every 9 minutes by Brian's watch. We always stress that every observer compares the arrival time of the flashes with his own watch, because otherwise we would have great difficulty in discussing just how long it takes him to see the other chap's watch. Now suppose that Brian also has a light, a red one, which he flashes every time he sees a flash from Alfred. Since Brian sees these flashes every 9 minutes by his time, he will flash his red light every 9 minutes. So this guy is flashing it every 9 minutes. By whose watch? Every 9 minutes by his time. Okay. The red flashes will then travel in company with the white flashes from Alfred, since they are emitted just as the flash of light from Alfred passes Brian. The red flashes will travel in company with the white flashes from Alfred, since they are emitted just as the flash of light from Brian. Just as the flash of light from Alfred passes Brian. We neglect the time it takes for him to flash his torch. These flashes from Brian traveling in company with the flashes of Albert's light will be seen by David, who receives the flashes of Alfred, the white flashes, every 6 minutes. Thus he will receive the red flashes also every 6 minutes. Let us put this a little differently. Alfred and Brian are separating at a certain speed, which we would have taken to be such that the interval between Alfred's flashes is multiplied the interval between Alfred's flashes is multiplied by 3/2 to give the interval between Brian's reception of the flashes, 9 minutes instead of 6. Brian is traveling at the same speed toward David as he is receding from Alfred. But now it is a velocity of approach, not a velocity of recession, and the flashes emitted every 9 minutes are received every 6 minutes, reduced by a factor of 2/3. So 2/3 of 9 minutes is 6 minutes. Okay. Correspondingly, had Brian flashed this light every 6 minutes, the flashes would have arrived at David at 4-minute intervals. Thus, if instead of a velocity of recession, one of approach is considered, the factor of 3/2 between interval of transmission and interval of reception is changed to a factor of 2/3. Thus, if instead of a velocity of recession, one of approach is considered, the factor of 3/2 between interval of transmission and interval of reception is changed to a factor of 2/3. Oh boy, that's not helping. Our results are quite independent of whether any of these inertial observers can be regarded as at rest. Are quite independent of any of these inertial observers, whether any of these inertial observers can be regarded as at rest. Indeed, the question of which of them is at rest does not make any sense. The only relevant matter is their relative velocity. What we have to remember is that if velocity of recession leads to some ratio of transmitting interval to receiving interval, then the same velocity but in approach applies the reciprocal ratio. Oh boy. Ugh. This is why it's good to have not static diagrams on your page. It's a little more helpful if we can be actually animated and you can see it. Otherwise, I have to try to conceive of it in my head, and it starts to get really hard. So word descriptions just kind of can be very, very confusing. It's much clearer in a picture. Now, I think I could kind of animate this like I did in my debate for some of the stuff, but this is just painful. This is really, this would take, I don't have the animation skills of a professional animator, but that's what it would take to really do this well from Bondi. Let me go to the diagram here. And what he's saying is, as I read it, let's assume this guy is stationary. And how would we get the rest of the guys to move? So if he's moving this away, it would mean we could also have the spacecraft and the guy and the Earth moving in the other direction while this guy is held as stationary. Oh boy. It could be one or the other. But this is where I have an objection. Seriously, this is where I have an objection to this. One of them has a clock that's ticking at a different rate. It really does matter whether it's this guy, whether the spaceship is stationary, or whether it's Alfred who's stationary. Their clock rates cannot be the same according to the Lorentz transformation. It really does. That's what as I look at this diagram, that's what I'm going to have to confront Dr. Phil with. From the outside, it may not, as he's describing it, you have these reciprocal ratios that are the same independent of whether you make this Alfred stationary or you make Brian stationary. So if Alfred is stationary, since there's a constant distance between Alfred and David, then David is stationary. If Alfred is the one who's moving, then David will move right along with him, but then this spaceship will be stationary. Now I have what I need to confront Dr. Phil with. It really will matter as far as the relativistic clocks in here. Okay. Thoroughly confusing. Okay, this is what I hate about some of the physics books. You really have to try to conceptualize what they're describing in words. It's almost impenetrable to try to just visualize it. So in the debate that I had recently, I was trying to visualize things, and it just got confusing as I tried to describe it to Rebecca, and we almost got into a pretty bad argument. And I said, Rebecca, let me just try to diagram this up. And so when I used the basketballs, she said that it made it really, really clear. And then also when I was describing the radar gun, it started to become really clear when it's animated. But when it's described in words, it's really painful. But in any case, let me just try to get through all this, and I'll read it some more, and then we'll wrap it up. I wonder what was on the docket now. Special relativity, general relativity, overleaf, and the Hubble constant. I won't get around to the Hubble constant maybe right now. I'll just touch on it. Okay. In more general terms, if Alfred had flashed his light at intervals h, then David would have seen the flashes at interval h, each flash taking the same time to reach him. Brian would have seen them at interval kh by his watch, so k is the ratio of the interval of reception to the interval of transmission. If Brian's flashes his torch at intervals kh by his watch, then these flashes traveling in company with those emitted by Alfred would be seen by David at intervals h, giving the reciprocal ratio of 1 over k between Brian and David. The relation between any two of our initial observers is completely specified by the ratio of the interval of reception to the interval of transmission. If this ratio is unity, as in the case of Alfred and David, then the two observers are at relative rest. If it is greater than 1, they are receding from each other, and if the ratio is less than 1, they are approaching each other. Note that the principle of relativity, by insisting on the equivalence of all inertial observers, makes it quite clear that the ratio must be the same, whichever of a pair of inertial observers does the transmitting. This is through the rule that our work on light differs so sharply from the work on sound, where it will be remembered the speed of the transmitter and receiver relative to the air also had to be taken into account. This is a lot to digest. This is so confusing. Man. So I'm going to have to talk to Dr. Phil about this tomorrow. I owe him to show diligence in this. As I'm agonizing over even the simple example, it reminds me of what it was like in school. It'd just be hours and hours of just banging your head trying to understand what was written and then working through the math. I mean, it was very, very stressful. So I have to look at what reciprocal ratio is. Okay, I will cover the Hubble constant briefly, because I'm going to be in a discussion about that soon. Do I have the picture of the Hubble constant? Yeah, I have one early here. Okay, so let me show that. This is from my cosmology book. Edwin Hubble's original plot of the relation of redshift, vertical axis, and distance on the horizontal axis. Note that the vertical axis actually plots velocity times redshift rather than z, and that the units are accidentally written as kilometers rather than kilometers per second. So this should be kilometers per second, kilometers per second. Now, I need to point something out. We could have we could have plotted this just as z without multiplying it by the speed of light. You could plot it just as z. Think about that. If you just had z, which is a dimensionless quantity, you would get just z in terms of whatever dimensionless number. So you get z and you say something like dimensionless, which is kind of funny, but okay. But if you insist on multiplying it by the speed of light, of course you would get kilometers per second. But let me show why that is somewhat superfluous. And this was the argument in the debate. So, see, you have the Hubble constant. Okay, so one way to look at this is you have z times c. I see, redshift. Z times c divided by the distance, which is r, equals the Hubble constant. And that's the redshift relation. That's right. Z times c over r always equals a constant. That's the Hubble law right there. But remember that the units of c is kilometers per second. And the Hubble constant is in kilometers per second per megaparsec. So if I can do this in latex, you could see that you divide kilometers per second by kilometers per second, you just get a number. And all this, as all this washes out, this eventually becomes per megaparsec. Z is, R is per megaparsec. Okay, so R will be in parsecs or megaparsecs. Hubble will be per megaparsec. Okay, so you can get this redshift relation in terms of units of megaparsecs to the -1. Just looking at that. I mean, you can factor out what I was trying to say in the debate. When you factor out all the units, it doesn't have to represent velocity at all. So you can make the argument the Hubble constant does not have. You're supposed to call it latex, not latex. Sorry. I always wondered why they don't call it latex. My professor says it's latex. And then now someone says latex. And then now I'm just going to call it latex. But Mr. Jetty's right. And I have to trust him. He speaks all these languages. So the fact that we make the redshift to be velocity is the only reason they say, well, the Hubble constant describes the space's expansion. And it's like, well, not necessarily. That's only if you interpret z as velocity. We don't actually know that z is the velocity. It's a conflation, and even Hubble pointed that out. You can just remove putting the speed of light there, and the units will be just in related to distance. It's just redshift, distance. Redshift, distance. Equating the redshift to velocity or relating it to velocity is superfluous. It is just redshift to distance. And I've said, let's say instead of Einstein's law of E equals mc squared, you said E equals m to the fifth, and call that the fifth power hypothesis, which is obviously wrong. And you'll say, the speed of light is what makes the fifth power hypothesis true. And it's like, you can take any observation. So we've made this observation of this redshift distance relationship, in that it's constant. You can make it into any law. You can use that figure and put it into your hypothesis and say that describes this or that. It doesn't make the hypothesis correct. All that we have done, and let me show this, all that Hubble did is notice you have distance and you effectively had redshift. He multiplied redshift by the speed of light, but you don't even need to do that. If he had just put redshift, dimensionless, you would see this this line here, and that slope indicates the Hubble relationship, the distance to redshift relationship. So I think Hubble's is basically the slope of that line. I think that's correct. So I'm going to mess this up, but I think 500 divided by 10 to the 6 megaparsecs, 500 kilometers. Okay, let's take 1,000 kilometers. 2 times 6 to the megaparsecs. I wonder what figure he got. Okay, so, look. He thought the numerical value of the Hubble constant was h of 500 kilometers per second per megaparsec. However, I think it turned out to be 50. So we had 500 kilometers per... Okay, so 10 to the 6 parsecs is a megaparsecs. So you say 500 kilometers per megaparsec. Rise over run. Yeah, that is the slope. The Hubble constant is a slope. But the actual figure eventually got to be like 70 plus or minus like 7 kilometers per megaparsec. Let me verify that in my cosmology book. Where did I put it? I misplaced it, and it's getting too late. It's time to turn in. I'll find that book. I think the figure is 70 kilometers per megaparsec. So I'd like to thank you all for joining me. We got to cover a lot of what I wanted. And I'll have a conference with Dr. Philip Dennis tomorrow, who has published in the American Physical Societies, the physical review letters of the American Physical Society, which is the #1 society in the United States for physics. Although I think the #1 physics organization is in Germany, Deutsche Physik or something. I can't pronounce it. Philip Dennis did something on general relativity and quantum mechanics. I saw the abstract of the paper. I couldn't understand a thing he said. He's brilliant. He's a mathematical physicist. So I look forward to talking to him. And so I will close out with just see if I have some. I'll close out with some soft music. Glory and honor to our Lord and Savior Jesus Christ. The Lord be with you all who love the Lord Jesus Christ. And as hard as it is to say, this is from the Bible. Let all those who do not love our Lord and Savior Jesus Christ be accursed. Maranatha. Take care, and God bless you all. Have a good day.